Number 7. Well, this is the kind of problem that most students aren't really all that fond of, where it's just a bunch of letters instead of having specific numbers in it. But, you know, the reason for doing this kind of thing is when you're done, you've found the answer to a whole class of problems. You've derived a formula that's good for anything like this, instead of just coming up with a number that's just the answer to one specific thing. So we have here an electric dipole, which means a pair of equal and opposite charges. And we're supposed to find the electric field vector at that point labeled P, which is on the, on the axis that's perpendicular to the line connecting the two charges, in terms of the various letters that are given in the problem, A and so forth. So it's the same thing pretty much as the previous problem that I did. You have to find, a few details are different, like now it's an electric field instead of being gravity, and we're finding the field vector rather than the force on something, but same general idea. You have to find the electric field from the one charge, as if the other one wasn't there, and you find the field from the second charge as if the first one wasn't there, and then superposition principle says add them together. So, and of course, you have to treat these as vectors. You have to take the directions into account. The magnitude of each field is going to be the same because you have the same amount of charge at the same distance, okay? The positive charge and the negative charge differ only in being positive and negative. They're the same number of coulombs, they're the same distance away. So for the magnitude, I don't need to distinguish between E1 and E2. They are the same. And as I said the other day, they're given by the Coulomb's law constant times Q over R squared, where little r here is not to be confused with the capital R labeled on in the question there. Little r is the distance from point P to the charge that's creating the field. So, like here's the picture from the question, and if you've got the charge up here and point P over there, little r is, so you got a triangle there, little r is the hypotenuse, capital R is this side, and half the distance between the two charges is A. Charges are separated by 2 times A. So little r comes from those other two things by the Pythagorean theorem. So this is the magnitude of each one. The directions, take them one at a time. For the positive charge, which is up there, point P is over here. An electric field points directly away from a positive charge. So the field of this one will be sort of in that direction there, to the right and down. or to sketch the components that go with it, kind of like that. X component to the right, Y component down. And I'll call that E1, the field of charge number 1. E is the length of this hypotenuse, the magnitude of the field. And I should have labeled it. Theta is that angle there. So hypotenuse times cosine gives you the adjacent side. Hypotenuse times sine gives you the opposite side. X component is positive, Y component is negative. The other one, point P is over here. Electric field lines point toward negative charges. So the field of this one is in that direction. Same angle theta, because the second charge is just as far below the axis as the first one was above it. E2, well, it's almost the same thing, except this time the X component points to the left. And so you get a minus sign there, and otherwise, same thing over again. Those are the two individual fields. Superposition principle says add them together. When you I won't argue they're probably having more fun than we are, but time and a place for everything. When you superpose them, when you add them together, the X components cancel each other out. They're the same size. One is to the right, one is to the left. So you get nothing for X. The Y components are also the same size as each other, but they both point in the same direction. So you've got 2 times T sine of theta for the Y component. Now, the way the game is played is when you get a problem like this one, you express the answer in terms of the things that were given in the question. You got little a, you got capital R, you got Q. Theta, though, theta was just something I came up with as I was working along through the problem. So before I can put a box around this and call it the answer, I have to substitute for theta. Also have to substitute for E, but I've got all of that over here. Theta comes off of this same triangle back over here that I, it's off the camera, but it was the first thing that, maybe I should move the camera for a moment. That angle there is the same as this angle here. There's where I labeled it. So from this triangle, you can get the sine of theta is the opposite over hypotenuse, A over little r. So substituting a whole bunch of stuff in. For E, the magnitude of each individual field, I've got this thing here, the Coulomb's law constant times Q over R squared. Sine of theta is equal to A over R, which simplifies a little bit more into this. And I'm almost there, except little r is also something that I came up with as I was working along here. If I'm going to have it in, like the question says, in terms of A capital R and Q, I got to put in the Pythagorean theorem to substitute for little r. And this will be the answer. One thing I want to point out, I'm kind of repeating something I said a few days ago. Coulomb's law gives the electric field around a point charge or a sphere. Well, I mean, this isn't exactly Coulomb's law. Coulomb's law is Q1. Coulomb's law is actually for the force, but the Coulomb's law electric field formula. This is Coulomb's law with one of the Q's canceled out of it. For other ways of distributing charge, other formulas apply, such as an electric dipole. Now, an electric dipole has no net charge, positive Q, negative Q. Your first impulse might be to say, oh, well, no net charge, they cancel out and there's no field around it. You could say that. You'd be wrong, but you could say that. But it doesn't, you know, Coulomb's law is an inverse square law. What we have here is if you are large distances away, like say the distance from the one charge to the other is a millimeter, and you're 5 meters away from the thing, okay? In that case, little a is small enough that you might as well just set it equal to 0 for all the difference it's going to make in the answer. At large distances like that, you've got r cubed rather than r squared, okay? The field of a dipole is an inverse cube. The field of a monopole, like an electron, is an inverse square. There are other examples. if you have a uniformly charged piece of thread, a long line of charge, the electric field around that drops off as 1 over r to the first power. And there are even other examples where it behaves in other ways. And we'll look at that more once we get several weeks further into the course. But for now, just keep in mind Coulomb's law, a point charge, in other words, a monopole, or a uniformly charged sphere. Here we have an example of something which is not an inverse square field. It's inverse cube at large distances, something a little more complicated if you're close to it. The last thing I stuck in this unit was just to explain the difference between conductors and insulators. I think the textbook has this somewhat further along rather than putting it right here, but yeah, I want to be able to toss the words around if I feel like it, and it doesn't take that long to explain them. I mean, a conductor conducts electricity and an insulator insulates. I thought I'd explain it in a little more detail than that, though. Everybody, I think, has some sort of a feeling for the idea that, you know, you've got metal up the middle of this wire here, and electricity will flow through that. And around the outside of it is something that won't conduct electricity, and that keeps me from shocking myself when I grab it like this. But what's the fundamental difference between those materials? Well, conductors, and metal is just one example of a conductor. There are plenty of other things that electric currents will flow through also. Conductors are any kind of a material that contains a lot of charged particles that are free to move around, okay? An electric current, which is something that I actually won't get around to formally defining for another week or so, but an electric current is a flow of charge. If I got out a bunch of these charged rods like I was waving around the other day, rubbed them with a piece of fur and handed them all out to everybody, told you run down the hall with it, that would be a small electric current. Okay, any kind of something well down into the microamps or even smaller, I'm sure, but a bunch of people carrying electrically charged rods running along, that would be a small electric current. Really, seriously. So, any material in which charged particles are free to flow that way conducts electricity. And anything, well, of course, all materials are made up of electrically charged particles. You've got protons in the nucleus and electrons in orbit around that in anything. But in insulators, everything is bonded nice and tightly in place, so nothing can move. Things like glass and porcelain and so on. So that's what it comes down to. If you establish an electric field in a material containing free charges, the electric field pushes on the charges and they flow, and that's a current. If you establish an electric field in a material which does not contain charges that are free to move, well, I mean, it still pushes on them, but they don't go anywhere. And so you don't have a flow of current. And I thought I'd bring along something for show and tell today to kind of illustrate the point. Add the water at the last minute because I already spilled it once today. I should probably wonder if I can get that to go down low enough. Yeah, that'll work. So I have here a power supply, which is kind of like a battery. It's a source of voltage. It's just batteries wear out and you have to buy more of them. And this thing's probably 40 or 50 years old and it still works. Plus you can dial up any voltage that you want to have. Battery, you're stuck, you know, if it's a 9-volt battery, you're stuck with 9 volts. But anyhow, The meter is here just so I can tell if I've got the voltage that I want to have. As far as a path for the electric current to follow, comes out of the positive terminal of the power supply, goes along this red wire. And here I have a little 50 milliliter beaker. And I've made electrodes by putting a piece of aluminum foil down each side of the beaker, okay? They're like about an inch apart. And what's in between them is tap water, or it is now anyhow. Pure distilled water is actually an insulator. I mean, water has sort of a reputation for conducting electricity. You know, don't use your toaster while you're sitting in the bathtub because you could get shocked, that kind of thing. What makes water somewhat conductive is any ions that are floating around in it. Minerals that might be in the water or stuff that it might have absorbed out of the air. But if you've got pure distilled water, maybe it isn't quite as good an insulator as oil, but it's an insulator. I mean, this is not distilled water, it's tap water, but just the same, that beaker there is good for something in the neighborhood of roughly 1,000 ohms right now. So if I turn on the power supply, you will notice the distinct lack of light coming out of the light bulb. Okay, the current comes out of here. There's actually a couple of milliamps flowing through the circuit right now, but it comes out of there, goes through the water, goes on down this wire, through the light bulb, and returns to the power supply to complete the circuit. Now, table salt. So, you know, sodium, it's been sitting around too long, it's all crusted up. There we go. As some of you may know from taking chemistry, salt is an ionic solid, which means that the chlorine atoms steal the electrons from the sodium atoms. And you end up with, if you dissolve it in water, you end up with positive sodium ions floating around in there because they've lost an electron, and negative chlorine atoms because they've gained electrons. So a whole bunch of electrically charged particles that are free to move around because they're just floating around in a liquid. They can go anywhere they want, just like a fish or something. So what I'm going to do is, as you probably have already figured out, I'm going to put the salt in the water, which makes the water a much better conductor of electricity because now it contains many more free charges than it did before. And for better dramatic effect, I'll turn on the light. It makes the light come on. Got to stir it around a little, got to wait a minute for the salt to dissolve, but yeah, see, there you go. And the salt might dissolve a little more even, which might make the bulb get even brighter, and it completely does not show up in the video because there's reflected glare off the countertop coming from that window over there. Well, anybody who's watching the recording will just have to take my word for it. I've got a dozen witnesses here. But as I added to the number of free charges in the water, it became a better conductor of electricity, and a lot more current started flowing through the wires. Now, you normally think of electricity maybe as being a flow of electrons, and that's what's going on. Electrons are what carry the charge down through the wires. But the charge-carrying particles are ions, not electrons, as the current flows through the water. Incidentally, just as a footnote, anybody who wants to see this could get out of their chair and come look. But yeah, the one electrode here is bubbling away like crazy. That's electrolysis. Passing current through the solution here is making it give off hydrogen and chlorine gas. And
That doesn't sound safe.
No, it's okay. It's not very much.
Is it safe?
Takes a big push.
It's like the science fiction movie where the guy gets out of the spaceship and goes, "Oh, I see there's air on this planet." Now I have to completely re-aim my camera again. Okay, well anyhow, that's the difference between conductors and insulators. Salt solutions, acids, anything like that contain a lot of free charges, conduct electric current. And time to turn the page. Hopefully you're keeping an eye on a schedule and you will be prepared to take quiz number 1 the next time we see each other. Everybody knows that Monday is Martin Luther King Day, right? You shouldn't come to class. Right.
I mean, there's a select few people, you know, that you would not necessarily be alone, but all of you can get in line and grab your dunce caps and then go home.
Potential is the title of section 2. This is another way of describing the strength of an electric field. Okay, we saw last fall that there are a couple of different ways of looking at the world. You can look at the world from the point of view of forces and Newton's laws and that approach. Or you can look at the world instead from the point of view of energy and the other conservation theorems. So, for example, if we had a problem where a box slides down a ramp, let's say a frictionless ramp like one of our air tracks, and you want to know how fast the thing is going when it gets to the bottom. One way of approaching it is you can draw the free body diagram and do the components of all the forces and put that into F equals ma and solve for the acceleration and then get the final velocity from that. Or, alternate approach that'll take you to the same answer, you can use conservation of energy. The potential energy that you started with up here equals the kinetic energy that it turns into down there. You solve for V final out of that. For that particular problem, the energy approach is probably a little bit easier. Well, it's sort of the same thing in the world of electricity. Sometimes you want to look at things from the force point of view. Sometimes you want to look at things from the energy point of view. If you want to describe the strength of an electric field based on thinking about forces, you had the electric field vector, E equals the force per unit charge. Looking at the field from the energy point of view, electric potential is the energy per unit charge. But I'm ahead of myself. That's like about 2 inches down the page. I started with just a quick little review for anybody who maybe has a short memory. Section 5, I think, in Physics 131 started with the concept of work. Work is the force times the displacement. How hard you push on something times how far it moves while you're pushing. To be precise, it's the dot product of those two vectors, which would be the magnitude of the one times the magnitude of the other times the cosine of the angle between them. It's only the F cosine component of the force that does work, the component along the direction of motion. Energy means stored up work. Anything that's capable of doing work possesses energy. And, well, actually, for the course as a whole, we saw several different examples of that. Kinetic energy was the work something could do because it's in motion. Potential energy is the work that something could do because of its position, and we looked at a couple of examples of potential energy: gravitational potential energy, elastic potential energy. Heat is also a form of energy. We looked at that a little toward the end of the course. Well, let's add something else to our list of different types of potential energy. Gravitational potential energy was the work something could do because of where it is in a gravitational field. The more you elevate it, the more work it's capable of doing. Elastic potential energy is the work something could do because of its position if it's attached to a spring. The more you stretch the spring, the more work it can do. Electric potential energy is the energy that something can do because of its position in an electric field. Just like gravitational potential energy, only instead of a mass in a gravitational field, it's a charge in an electric field. So in a strong electric field, a test charge will be capable of doing more work than it could in a weak electric field. Just like a mass in a gravitational field, same thing is true. But the amount of work something could do, like electric field around this rod, and I've got this charged ball. The amount of work it could do in moving maybe from there to there depends not only on the strength of the field it's been moving through, but also how much charge I've got on that ball. If the ball has twice as much charge on it, it can do twice as much work. The thing that's a property of the field only would be the energy per unit charge, and that's called the electric potential. It's potential energy per unit charge, actually. So I should make a spot to write that down. Potential. You can talk about potential in other kinds of fields also, gravitational potential, for example, but today we're interested in electric fields. So potential energy per unit charge, this would be the electric potential to be precise. We're going to use the letter V to stand for that. We're going to use the letter U to stand for potential energy, same notation I used in Physics 131. The E subscript on the U is to label it as electric potential energy as opposed to gravitational or some other kind. So potential energy per unit charge is the potential, the unit to measure it in. Energy in the SI system is measured in joules. Charge is measured in coulombs. So the SI unit for potential is a joule per coulomb, as is often the case. It's given a name of its own. A joule per coulomb is better known as a volt. After Alessandro Volta, who invented what we now call the battery in the late 1700s. I don't actually know why they dropped the A off the end of his name. It's not like Volta was such a terribly long name, shorter than mine, for example. But, well, for whatever reason, they did it. It's a volt, not a volta. Frequently, what you find yourself talking about actually is the difference in potential between 2 points rather than the absolute potential somewhere. And so that's the same thing just with deltas. Potential difference, delta V, is delta U over Q. Technically, it would be the potential difference between 2 points. That's the work done per unit charge. So in practical terms, I guess I'm jumping a few lines down the page here, but that doesn't actually hurt anything. Cars are 12 volts. Your house is 120 volts. There's also the matter that your house is AC and your car is DC, but let's save that story for another day. If you pretend your house runs on direct current like your car does, okay? I mean, it's not that hard to get 120 volts of direct current. You just get 10 car batteries and hook them all up in series. But the difference is that if you've got a light bulb and you connect it to 12 volts, every coulomb of charge, remember a coulomb of charge amounts to a certain number of electrons. I think it's whatever the reciprocal of E is. I think it's around 6 times 10 to the 18th. I'm not going to bother to punch it up, I'm pretty sure. So it's around 6 times 10 to the 18th electrons, carries 1 coulomb of charge. That number of electrons flowing through your light bulb in a 12 volt circuit delivers 12 joules of energy to the light bulb. A volt is a joule per coulomb. The exact same number of electrons flowing through a light bulb in a 120 volt circuit delivers 120 joules of energy. Same number of electrons delivers 10 times as much energy because the electric field is pushing on them 10 times harder. At the higher voltage, you create a stronger electric field inside the wires. This is the reason why if you take a light bulb that's intended for use in a car and hook it up to house current, you don't even see it come on. I mean, if you've got some sort of infrared detector, you might notice a little bit of infrared coming out of it, but as far as visible light, it's not going to get nearly hot enough. If you do it the other way around, if you take a 12 volt bulb and you hook it up to house current, put 120 volts on it, well, that's going to put 10 times as much energy in the light bulb as it was designed for, which will immediately vaporize the filament. So it's just going to go off like a flash bulb and then be dead, okay? So, I mean, so a volt is a joule per coulomb. It tells you how much energy each unit of charge carries. The higher the voltage, the stronger the electric field, and therefore the more energy delivered by each electron or each coulomb of charge or whatever amount of charge you want to talk about. Going back to the electric field vector, E, like I talked about in section 1. That was measured in newtons per coulomb. Well, now having introduced this unit, the volt, it only takes a couple of lines of manipulations to show that newtons per coulomb is completely equivalent to volts per meter. A newton per coulomb times meters over meters, and then a newton times a meter is a joule, and a joule per coulomb is a volt, and so on. So calling it newtons per coulomb is kind of a nice way to look at it when you're thinking about what does the field vector actually mean, the force per unit charge. Calling it a volt per meter is kind of more practical for laboratory work, because if you've got two metal plates that are a known distance apart and you apply 100 volts to them and want to know the strength of the electric field in there, well, volts divided by meters gives you volts per meter. More on that coming up before too long. So newtons per coulomb, volts per meter means same thing. Which gets us down to example number 1. So this is a conservation of energy question. I should probably move this back over. One thing I talked about in physics 131 is, what if I drop this eraser and I want to know its speed when it hits the floor? Well, you can figure that out using conservation of energy. Potential energy that the eraser has up here is equal to the kinetic energy that it has when it reaches the floor. You set mgh equal to 1/2 mv squared, solve for V final. Potential energy initial equals kinetic energy final. This is the exact same problem, only it's an electric field, it's a charge in an electric field instead of a mass in a gravitational field. But the underlying idea is the same, that as the thing moves, potential energy changes into kinetic energy. So you've got an evacuated vessel of some sort, because if there's any air molecules for the electrons to run into, it kind of just spoils the whole party. So you get all the air out of there so that the electron doesn't collide with any air molecules along the way. And well, a little while I'll get to where the electron would come from. For the moment, let's just say it mysteriously appears there near the negative plate. All you have to do to make something like this is you have two chunks of metal, you put them in a glass tube, and then you can melt glass with an acetylene torch. So you just seal the ends by melting the glass after you've put your wires through there, pump out the air, and there you go. So reaching in my pocket for the marker, but that's not what we're doing this time. Conservation of energy. Let's write it this way. I think that'll be the most convenient in this case. The total energy, kinetic plus potential, the total energy of the electron does not change. And so change in potential energy, as the electron moves, its potential energy decreases, so that term would be negative, plus the change in kinetic energy, as the electron moves, it gains kinetic energy, so that would be positive. The total change of the two kinds of energy is that it doesn't change. Incidentally, be careful of your handwriting. Capital V for volts little v, or kind of a script v, whatever you want to call that. Big V for volts, little v for velocity. They're going to be in the same equation. The change in potential energy, we're going to get that from this. question says there's 1,000 volts between these two plates. That goes in for delta V. Charge on an electron is something you can look up. And so delta U equals Q times delta V. So you take the definition of potential difference, you rearrange it a little bit, and that, by the way, this is one of those things that you're supposed to remember. I want you to actually know what a volt is instead of having to look it up. That is probably the reason why when I ask questions on a test similar to this example that I'm in the middle of right now, people, you know, people don't do as well as they do maybe on some of the other questions on the test. And I think it's because you can't just pull out the formula sheet and go, oh, I don't know anything about this, but that looks like a promising formula there. It's got the right letters in it, I think. You actually have to know what a volt is. And that, anyhow, be prepared for that. A volt is a joule per coulomb, potential energy per unit charge. Rearrange it, and delta U is Q times delta V. The change in kinetic energy from physics 1, that's something else you're supposed to know actually, is the formula for kinetic energy. From last fall, it's 1/2 mv squared. So the change in that, final minus initial, and actually it started at rest. So the initial energy is 0, initial kinetic energy. Fill in the other numbers, solve for the final velocity. Charge on an electron, negative 1.6 times 10 to the negative 19th of a coulomb. Potential difference. As the electron moves, its potential will increase. Now, the way things are defined, if you release a positive, remember everything's defined with positive charges in mind. If you release a positive ion in this electric field, the direction it will move will be toward a lower potential. Just like if I drop that eraser, it'll move towards a lower elevation. Positive charges move toward a lower potential. Electrons are negative, so they're backwards. It's going to move toward a higher potential. So this is an increase in voltage, which is why this term is positive. The mass of an electron comes from the same table where I got the charge. Final velocity is my unknown. Well, maybe I can skip writing down a line or two of fairly obvious math. You multiply that times that, you multiply that times that, and you divide, and you take the square root, and when the smoke clears, this thing is moving at 1.87 times 10 to the 7th meters per second, which is really fast, actually. But you see, electrons are very lightweight. And so it doesn't take an awful lot of force to get them up to a pretty respectable speed. They don't have much inertia at all. Okay, well, I've still got a couple minutes to explain to you where that electron would have come from in the first place. Vacuum tube technology today is, I'm not going to say it's obsolete. That's not true. It's become more of a niche technology, or is it pronounced niche? I can never figure that out. Anyhow, it's become sort of a niche technology as opposed to like in the 1950s when they were like the backbone of the electronic industry. As an example, I have here an old style TV picture tube. Like, you know, maybe some of you still have an old TV in the basement or an old computer monitor or something like that before they came out with the flat screens. If you go back into the 1950s or even into the early 1960s, actually, it wasn't just a picture tube. All of the rectification and amplification and everything else was done with vacuum tubes. They were able to get around that by some point in the 1960s, but a picture tube was more problematic, and they continued to use a vacuum tube for that up into the, you know, somewhere around the turn of the century, actually. But even today, now the TV picture tubes are gone, probably the most common around the house type example of a vacuum tube is the magnetron that's in your microwave oven. It's the thing that produces the microwaves. Or if you just want to look at it from a physicist's point of view, for example, those big particle accelerators, you know, the Large Hadron Collider over in Europe, or some of the other colliders, the linear accelerator they have in California, or the rings that they have in Fermilab or Brookhaven or places like that. They are basically enormous vacuum tubes that are just, you know, miles across. So it's, plus a couple of the experiments we do in this course involve vacuum tubes, and it's good if you understand how the apparatus works. So here's a short summary, and then I better be quiet and let you do the lab pretty soon. But vacuum tubes are an outgrowth of light bulb technology, okay? Just like in a light bulb, you have a little piece of wire that you get hot. And if that filament gets hot enough, electrons will basically cook off of it. It's a process called thermionic emission. The heat provides the necessary energy for the electrons to escape into the surrounding space. This is why vacuum tubes are power hogs compared to transistors. You have to keep that filament hot all the time, and that takes, you know, if you decide to go on a picnic in your 1954 DeSoto and you want to have some music while you're having your picnic, so you leave the radio on in the car the whole time, when you decide to drive home again, there's a pretty good chance your battery will be dead because the radio has sucked so much power it's killed your battery. Because in 1954, it would have still been a vacuum tube radio, okay? So that's where the electrons come from. To get them moving, because most vacuum tubes make use of an electron beam to accomplish some purpose or other. To get them moving, that's pretty much the example I just went through. You have a set of plates that you apply a high voltage to, like this 1,000 volts I had here. That's another disadvantage of vacuum tubes compared to modern transistors. You not only need a lot of power for the filament, but to get that accelerating voltage, you need a transformer to create the high voltage, and they're kind of bulky and heavy also. You get an old radio from the 1930s, and it's about, you know, yay by yay by yay. That's part of the reason why. So the electrons cook off the filament, get them moving something like 1,000,000 miles an hour with a high voltage like this. And where in this simplified tube here, I just had them crashing into the positive plate. Well, in an actual useful vacuum tube, you have a hole in the positive plate. Some of the electrons shoot through the hole and out they go into the main part of the vacuum tube. So that's basically how an electron gun works, okay? In the case of a TV picture tube, you can then deflect the beam up or down by passing it between a set of charged plates. You can also deflect the beam right or left by passing it through a differently oriented set of charged plates. Or it can be deflected magnetically rather than electrically also. The screen over, this is the front of the vacuum tube over here on the right. In the case of a TV picture tube, it's coated with a phosphor that glows where the beam hits it. You sweep the beam across the screen very rapidly, turning the brightness of the beam up and down as it goes, and that's how you create the picture. Well, in a black and white TV. For color, you use 3 beams instead of 1. And, anyhow, that's that story. So I need to stop the recording and get out the answer sheets. For today's lab has 2 parts. I've got a full 6 setups for the one part, but the Coulomb's law experiment, which is at that table, and that one, I only got 3 setups because it didn't seem like it wasn't exactly a cheap setup. And really, it takes just about exactly half the time to do the one part of the lab and pretty close to half the time to do the other part of the lab. So why not just tell people to do half the lab and then switch? Probably easier to move the people than the equipment. So just as soon as one of those Coulomb's law setups becomes available, just switch to that table and do the other half of the lab. And the answer sheets, what are they with the answer sheets? I stuck them under my notebook here. There's an answer sheet and there's a piece of graph paper. And that's these.